as we finish that, we'll go to current slide. And I'll also turn on the projector. Now, one other issue, and it's just a sort of a minor one, but just wanted to let you know, in case you were looking and wondering. You know, I was out of town 2 Fridays ago. Not out of town. Not on campus 2 Fridays ago because I had an infusion. Had to be at the clinic at 6:30 and didn't get away till 4:30. So no way I was going to be on campus that day at all. Last Friday, I was on campus ever so briefly, a little before 6 in the morning until a little before 6 in the evening. Okay? But of course, no students were here. I did get a little bit of grading done while I was waiting for the other instructors to show up for us to go to Opelika. Like I said, I got there a little before 6 and we left about 6:10, 6:15, something like that. So I got maybe less than 30 minutes of grading done, but I got some done, but nothing that you would have seen or realized. And I didn't see any students then. And then we didn't get back, like I said, until almost 6 in the evening, so I wouldn't have seen any students then either. So what that leads me is to this Friday. Okay. Now usually on Fridays I get I try to get caught up on grading. I try to get all the grades in Blackboard, and I try to get all the attendance in. Okay. When I had my infusion, I got all the grading done and the stuff in Blackboard and the attendance done because I was sitting around waiting for parts of the time, and until the drug knocked me out, basically, I was able to stay. And then the internet cut off some, but I got all the stuff caught up. Last Friday, absolutely not, because I was driving for 2 hours plus, then we were in meetings constantly, then driving 2 hours plus back, and then stuff. So I got a little more grading done on the weekend, but I didn't get anything put on Blackboard or attendance. So if you can notice that and saw, hey, I turned this in, but I haven't seen a grade yet, that's why. Okay, I've got all your stuff graded to date, but I don't have it on Blackboard yet. Maybe. Can't remember in this class whether I've got it there or not. And your attendance, I have some on attendance, but not all. So this Friday, finally have a chance to catch up? I sure hope so, okay, because I've got my annual physical this Friday at 8 o'clock in the morning. So that means I have to be at the clinic by 7:45, which I won't be on campus then. But hopefully the physical won't last more than an hour. And if it doesn't, then maybe I'll get away in time to be on the campus by 9:45 or 10 o'clock or something like that. So if that's the case, I will be there from something like 10 till 1. Hopefully that'll give me enough time to get things caught up. However, the last time I went for a physical, I also got my flu shot that same time. And the gal, when she was the nurse, sometime after she finished giving my shot, I guess she was throwing away the needle and she nicked herself with it. So that meant that they had to do blood work on me to make sure I didn't have anything that she could have gotten exposed to. And of course I didn't, but they had to verify that. That's just the rules they have. So I had to stay late that time because they had to work me into the lab schedule to give me that. Hopefully that won't happen this time. I've already had my flu shot. Hopefully they won't have to do any needles, and hopefully I can talk them into waiting and do the lab work until I see my hematologist next month. And I think my internist is happy to do that, only do one stick. He'll just put in his orders to be with the hematologist orders, so they'll just do one stick and get all the blood at once. Maybe all the blood, but it doesn't matter. So anyway, so that's where things are sitting now. Hopefully I'll be able to get grading done and some input done while I'm in the waiting rooms, and then when I get back to campus, finish it up. All right, any questions or anything up till now? And for those who are graduating, did you find out anything on that? Did you ask anybody? You were asking me about the
test?
no, weren't you asking about the attendance?
Marcus? He also graduated?
Oh, yeah, the market. Yeah, right. Oh, okay. That's what I thought it was, but because they had the graduation meetings listed separately too, so I didn't know what they were doing with that. But I would check at the registrar's office just to make sure, okay? Because I don't want to lead you astray. Okay. Jonathan came in, and Nigel came in. So the faithful four are here. The two that are trying to do it remotely haven't heard from them. Well, I heard from one last week. Hopefully, I'll hear from the others soon. Any other questions? And you said you've already graduated, right? Okay. Did you do the CAP test? It's the Collegiate Academic Achievement Proficiency or something like that. Okay, you graduated when? Past term. Okay. If you want to take that test, I don't know if you do or not, it's just a standardized test. It can't hurt you in any way, but it can, if you get good scores on it, you can record that and do applications on it. Might get you some extra bonus points or something, but you can check and sign. Well, check at the registrar's office, and they'll probably send you around to see Miss Herndon. Check with someone down there to see if you should take that test or not. I imagine it'll be optional for you, and if you don't mind doing it, I don't think there's any cost to it. It's just going over and doing it. Okay. It gives us some data, and it might actually help you some too. But it can't hurt you. All right. Last time I was telling the others, I was the only one in the room, and I got as far as I could. And I believe I got on page 65 in 2.4 exact equations. Okay? And it got down to a sort of a paragraph just below the middle of the page that says some observations are in order. If you've got your books, page 65, about 2/3 way down the page, between half and 2/3 down, some observations in order. First, it is important to realize that the expression, and we developed this expression last time. I was the only one in here developing it, but I developed it last time. So if you check the YouTube video, you hopefully would have seen this. We worked down to an expression of this: n of xy minus the partial with respect to y of the integral m of xy dx, sorry about that, dx okay. That's in the last example we did, equation we did, equation 6. That was what your g prime of y was, okay? Now, that expression, okay, this looks like there's an x and a y in it. This is taking a partial with respect to y of a function with xy in it, but you're integrating over the x, and all you'll get out of this is a function of y, and you take the partial of that with respect to y, and then you take this n of xy minus that. Well, looks like you still could have some x dependence there, but that part of it is strictly with respect to y now. That's the only thing you have, okay? Okay? Now, the only reason they say there's no x dependence is if you look at that equation that they're referring to, and I should have written this, that's what g prime of y is, okay? There is no x dependence in the g prime of y, okay? So therefore there can't be any elsewhere, which means this n of xy, the x dependence must have deteriorated or disappeared there somehow, okay? Now, here's what they say. That expression we had, take the partial of that with respect to x, of this whole expression, n of xy, minus the partial with respect to y of the integral of m of xy dx, okay? And that would be, if you're taking the partial with respect to x, that would be the partial of n with respect to x minus the partial with respect to, now here's something they've done. Remember, okay, time out. One, so that's in here now, no, yeah. You're the only one, I think, who hasn't finished Cal 3. You're still in Cal 3. The others have finished it, okay? We haven't done partials in Cal 3 yet. So you may not know this a priori. You guys should know it already. But let me explain this. When you're taking partial derivatives, if you've got good continuous functions and everything's differentiable, it doesn't matter the order you take it, the partials. So this is partial with respect to x of the partial with respect to y, but you can take them in any order, so we're going to do the partial with respect to y after we do the partial with respect to x, and they're putting that then here, partial with respect to x of the integral m of xy dx, okay? Now, if you do that, this gives you partial, sorry, wrote it in the wrong place. Not that it matters, but I just wanted to keep it so it makes more sense logically. Partial of n with respect to x minus, now, take a time out and look at this. Here we have the derivative of the integral of the function with respect to x. Okay? This is the derivative with respect to x, integral with respect to x. They undo each other, and what you're left with then is just m, because the derivative, the partial of the integral disappear, and you're left with m, and that's the partial with respect to y of m partial with respect to y of m, okay? And these are equal to 0. Why is it equal to 0? Because this has no x dependence. And what you're doing is then taking a partial with respect to x of an expression that has no x dependence. So it has to be 0, and this leaves you with this result. This is key. This is very key, okay? In fact, this is the linchpin for which you do exact equations, okay? Right there, all right? So that's your first observation, okay? Partial of n with respect to x minus the partial of m with respect to y is equal to 0. Secondly, we could just as well have started the foregoing procedures with the assumptions that if partial of f with respect to y is equal to n of x, y. Now that was going way back, as in almost the top of page 65, where we started with the partial with respect to x of mxy. Rather, we start with the partial of f with respect to y is equal to nxy. After integrating n with respect to y, then differentiating the result, we would find the analogs of 5 and 6, this being 6 here. 5 I didn't write down, I guess I should. Yes. Let me write it here. F of xy is equal to the partial, now this time I'm doing with the n of xy dy plus h of x. Okay, well, no. I've swapped them, okay? So if we swap this, and then like I've just done swap that, then the next step would be integrating this with respect to y, and that would give me f of xy, because you integrate that with respect, in other words, put your dy over here, integrate this, integrate that. That would be the integral of n of xy dy, just what I had there, plus some h of x, which is, because these are partials, when you're integrating, you're only integrating with respect to one variable, that'll wipe out your y's here, because you're integrating with respect to y, and leave you only x's, but then you would have a plus c, constant. But because the x, you're integrating with respect to y, the constant could be a function of x. It doesn't have to be a pure constant, so that's why the h of x is thrown in there, okay? Now, then, as we did before, you'll have to listen to the last lecture, h prime of x would then be m of xy minus the partial with respect to x of the integral n of xy dy, which basically has you right back up like this was the h prime of x. This is just like that g prime of y, but we've reversed the m and the n, okay? And what you're taking the partials with respect to, okay? Now, they do all that, carry you through all that, make you suffer through all that, and then they say, in either case, none of these formulas should be memorized. Don't. This is just showing you the rationale for doing it, okay? Now, how you do it, you actually do the operations rather than writing all those long, complicated things out. Let's do example 1 and see if we can figure out how to do that. Okay, now, I know y'all weren't here last time, so I will be a little redundant, I guess, and go back over a few things. Here's what the example 1's requirement is. Solve 2xy dx plus x squared minus 1 dy is equal to 0. Okay. Now, just a couple things to note. Okay? And I hate to say it this way, but it is what it looks like. If you were to write this rather than a differential, this equation in terms of differentials, but in terms of derivatives, then you would have, this is not how you're supposed to think of it, but how you usually think of it. Divide everything by dx. Okay, now that's not what you're doing, but just imagine that. This would be x squared minus 1 dy dx plus 2xy is equal to 0. Okay? Now, that is a separable function. We could solve it using separation of variables, and you certainly can. Okay? This is also a form of a linear function. Then you would have to divide both things by this, and then you have dy dx by itself plus 2x over x squared minus 1, y is equal to 0. That's a linear function, and you could do that by the technique we just did earlier, which is integrating factor, okay? When you go to do that, that's going to be a fair amount of work. Or, since it's already written in this form, and this is a function of x and y, this is technically a function of x and y, there's only a function of x, this is also what they call an exact form, okay? If the following condition is met, okay? Now, I don't know if you listen to the things or not, but the YouTube video, but if you haven't, here's what the requirement is. Okay, first, this form just like this, m, so this is going to be your m of xy. It's going to be this thing. Your n of xy is going to, let me make sure I got it in the right order. Yeah, that's going to be this thing, okay? And you got to equal to 0. This is an exact differential in some region R of the xy plane if it corresponds to a differential of some function f of xy as defined on R. The first order differential equation of that form is said to be an exact equation if the expression on the left-hand side is an exact differential, okay? If it's an exact differential. The next theorem, that was definition 241. The theorem 241 says for the criterion for an exact differential, if the partial of m with respect to y is equal to the partial of n with respect to x, then you have an exact differential. Let's see if that's the case. What's the partial of m, which is 2xy, with respect to y, always the opposite of that one, is that equal to the partial of n, which is x squared minus 1, with respect to the opposite of that would be x. There's the question. Now, for De Silva, since you haven't had this before, let me review this. When we take a partial of an expression with respect to one variable, we treat the other variable as if it's a constant. Okay? So the partial of this expression with respect to y, since x is independent of y, you just treat that as if 2x was just some number. Okay? So what would that be? Partial of 2xy with respect to y would be 2x. Just treating x as if it's a constant, that would be some constant times y. Partial of that with respect to y would be whatever that constant is, right? What would be your partial of x squared minus 1 with respect to x? 2x. Yes! Those are the same, therefore this is an exact differential. Okay? So, that's the criterion that must be met. It was met. Okay? Now, method of solution. Okay? Now, again, sort of go through the steps here. If it meets that criteria, okay, then there is a function f, which isn't listed here anywhere. A function f, which is a function of x and y, so that the partial of f with respect to x, okay, is equal to your m of xy. Right? There's got to be some function f, okay, whose partial with respect to x is that, okay? Now remember, your m of xy is this. It's the thing that precedes the dx, okay? So what we have here is the partial of f with respect to x is equal to 2xy. This is driving me nuts, okay. All right, now let's do that. let's rewrite this as partial of f is equal to 2xy. And since we're separating them, we'll call that a dx now, okay? And we'll integrate both of these, okay? Now, when you're integrating what was a partial, and you're integrating with respect to x, you can let that y's be constant. Same type deal. So this gives you f, that function f as a function of x and y would be equal to, okay, and again, the y is a constant, so you can pull it out of the integral if you want to, okay? But what would be, if you did pull it out, what's the integral of 2x dx? Second? Antiderivative of 2x dx. Second? I see your mouth moving. I can't hear what you say. Now x over 2. Okay, it's 2x squared over 2, which would just be x squared, right? Because derivative of x squared is 2x, right? So the antiderivative of 2x would be x squared, right? So it'd be y, or x squared y, plus, and you're taking the integral with respect to x, you may still have a g of y left over. Whereas we would put plus c, okay? But remember, we counted our y's if they are constant, so any function of y would also be a constant. So we put a g of y there, okay? So this gives you what we got so far, okay? That function, f of xy, would be x squared y plus g of y. Some constant function that has no x dependence, okay? Now, we said the partial of f must be your m of x with respect to x. The partial of f with respect to y must then be your n of y. So let's do that. And here you got your f of x now. So the partial of x squared y plus g of y, that's your f of xy, with respect to y, must equal x squared minus 1, right? Okay. Remember, the assumption was there has to be an f in there. So the partial of f with respect to x is this thing, and the partial of f with respect to y is that thing. Because here's what we're gunning for, folks. The partial of f with respect to x dx. Yuck, I always do that. I don't know why. Plus, I'll clean that up just a little bit in a second. The partial of f with respect to y dy is equal to 0, okay? If you've got something like that, there is some function f that satisfies that equation, okay? If you can find an f that satisfies that equation, you've got your solution. So what we first did was your partial of f with respect to x must be that thing. So we carry that through as far as we can, we get this. Now the partial of f, the same f, that's the same one we had here. Now we just know a little bit more about it. Partial of f, this with respect to y, must be that thing, okay? So that's what we're doing now, okay? I'm going to take this scratch work out of the way here because that's what we were gunning for. I wanted you to see that form and see that it does make sense, so to speak. Okay. Now, let's do the same thing we did before. Partial of x squared y plus y g of y. I'm sorry, I can't read my writing. Okay. Oh, dy, sorry, dy. Okay. Let me clean that up a little bit. Sorry, it's really ugly. Too much erased. Okay. And we'll integrate both sides of this. So this leaves us integral of the perfect derivative would be x squared y plus boy, I think I'm skipping a step here. Oh, I'm sorry. You don't go back and integrate. I got carried away. Sorry about that you've written things you don't need. Sorry. Okay. Okay. We take a derivative of this thing with respect to y. Well, derivative of the first term with respect to y is, remember you treat x as if they're constants, just x squared. Plus, and take derivative of g with respect to y, and that's g prime of y. Okay? And that's supposed to equal x squared minus 1. Right? Well, guess what that says? Subtract that x squared from both sides. That's taken care of. This just says that g prime of y is equal to a minus 1. So what you reckon g would be? This is that just about. G of y would be minus y. Right? Because you have to have a minus. Derivative of minus y is minus 1. Right? Okay. So that's what your g. Well, go back here. F of xy is equal to x squared y plus, and your g of y is actually minus y. Okay? Now, at this point, and not until you get to this point, that you can say is equal to c. Let's see. Maybe we should have done it just a step or two earlier. Okay. Yeah. X squared minus y. And this, you could put plus c, or you just separate the c out there and say c is equal to c. It doesn't matter. You could put plus the c prime or c1, and then put it on the other side of the equation and have it be a c. I mean, that's just how they do it. The implicit form is that. Okay. The explicit form would then be, you can solve this for y. Factor out a y from both sides, and you get x squared minus 1 is equal to c. So then y is equal to c over x squared minus 1. Okay? So there's your one parameter system. Wait a minute. How did they pull that sneak on me? Okay. They did something tricky here that is not, I don't see how it's justified. We got x squared, I mean, I can see it may be true. X squared y minus y is equal to c. Sure, we got that right here. And by the way, where did that c come from? If you go back, what's that? Yeah, it's a constant of integration for sure. But I'm trying to find exactly where they first snuck it in. And it's much further back than this section, or a little bit further back. Ah, there it is, there it is. It's the bottom of page 63, okay? It says, in the special case of where f of xy is equal to c, where c is a constant, then you have this being true, okay? Because when you take the derivative of both sides, that's where your equal 0 comes from, where this equals 0. If there was a function, f of xy, that fit, remember when I had it up here, partial of f with respect to x dx plus partial of f with respect to y dy equals 0. Okay? If there was a function like that, then the f of xy must be some constant. Because when you take the derivative of the left-hand side, you get df plus df is equal, integrated that, you get f as a constant. So the next thing after that would be that f of xy is equal to some constant c. Okay, so that's where you got this. That f of xy, which you found to be that, is equal to the constant c. Okay, you can think of it as a constant of integration, but yeah. Now, when you factor out the y, that gives you what we have below here. Now, what I know why they did it, but they don't give a very good rationale of why they did it. In fact, they don't say anything about it, except the explicit form of the solution is easily seen to be. Whenever they say easily seen, it's probably not that easy to see, okay? That's usually a dead giveaway, okay? Because when you factor out the y, you have y times x squared minus 1 is equal to c, and then divide both sides by x squared minus 1, that would give you this. But what did they divide by? They divided by 1 minus x squared. Now, why did they do that? Okay? It's not at all clear, okay? I'll tell you why I think they did. You want an interval that this thing's going to be true, okay? Now, when you divide both sides by x squared minus 1, you can't divide by 0, right? So therefore, x equal 1 and x equal minus 1, no, yeah. Because if you had that, then this would be 0 times y would be a constant, that would be 0. So that's not a very interesting problem, okay? But you want an interval over which x is good. And the only interval over which this would be good is where x squared is greater than 1, right? Because then you could divide by that. Or where x squared is less than 1, okay? That would be okay, but not equal to 1. But, that would give you, what it would wind up giving you are values of x less than minus 1 at the same time greater than plus 1. You can't have that. what you can have is this. You can have x being between plus or minus 1, then that has you an interval over which you can deal with it. So basically, they kind of said here, we don't like that being c, let's make it a minus c, then we can flip this and make that a c again, and then you come out with this one. And I can see that's why they did it. That gives you an interval from minus 1 to plus 1 that is perfectly fine. Not the ones out here that you can't satisfy both of those, but the one in here. Now they did nothing to, they said is defined on any interval not containing either plus or minus 1. So that says it could be to the left, middle, or out to the right. But they, anyway, why they flipped the sides, I don't know. Okay? Doesn't hurt to do it, but I don't know why they did. The solution of the differential equation in example 1 is not this. That's not the solution. Okay? Rather, it is f of this equals c. I'm sorry. It's not this. That's not the solution. This is the solution. You don't just find the f of xy. You made up f of xy. Okay? You said, let there be an f so that this is true, and you found out that's what f it was. That's not the solution. It's that f of xy has to equal a constant, so this ain't equal constant. That's your solution, not get the f of xy out of there. As soon as you found out what it is, throw it away and just use that. That equals c, that's your solution. Okay. Now, how you play around with it doesn't matter. You could have left it in this form here and said this works for any x less than 1, between minus 1 and 1, and greater than 1. Just like you could say the same thing here. This works with x less than 1, between minus 1 and 1, and greater than 1, as long as x squared is not equal to 1, and therefore x isn't equal to plus or minus 1. Any of those intervals that contain those three intervals, that's fine. So it really doesn't matter which form you left it in. They just did not give you any rationale for splitting like they did. All right. A lot of blah, 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 right? Let's go back and see if we can repeat this with example 2. Okay? Let's solve this one. Oh, this looks interesting, doesn't it? E to the 2y minus y cosine xy dx plus 2x e to the 2y minus x cosine xy plus 2y dy equals 0. That looks fun, doesn't it? Now, if I ask you what's the difference between the last one and this one, yeah, there's a ton of differences, right? But here's one of the main ones. Can you solve that one using separation of variables? How are you going to separate an xy inside a cosine xy? It ain't going to happen, okay? And you got that on both sides. There's no way you're going to. Can you write that as a linear equation? So if this is solvable, the only way that's going to be solvable is by exact solution. Okay? Now, where do we begin? What is this called? M of xy. What is this called? N of xy. And what's the condition for this to be solvable? The equals 0, we got that part. The partial of m with respect to which y must equal the partial of n with respect to x. Doesn't matter what they are, they just got to be equal, okay? So we need to do that. The partial of this with respect to y. What would that be, by the way? Partial of that m with respect to y. That's the e there. What's that? E to the 2y. That's a good way to begin. Times 2. Chain rule, right? Okay. Got that. Minus partial of that term with respect to y. Looks like a different product rule to me, doesn't it? Same rules work in partials. Okay. And what would that be? Okay. Minus, if, with respect to y, if you do that with respect to y, it's 1. So that's just going to be a cosine xy. Plus, very good. Got to have that y times derivative of that. Now, the derivative of cosine is minus sine. Now, you take it with respect to y, remember? So that's going to be a minus sign. That's why I changed that to from a minus to a plus. So that'll be a sine xy times chain rule. Wait, you're integrating. Okay, wait, don't. No, you're differentiating. So chain rule. You did a product rule here. The derivative of this times that plus this times the derivative of that. And you had a minus sign in front. And derivative of cosine is minus. So you still got the chain rule derivative with respect to y of xy. Gives you another x, right? So the partial or derivative of sine is of cosine is minus sine. Okay, you have the first times derivative of the second. Derivative of the second is derivative of cosine is minus sine, so that made this a from a minus to a plus. Sine of xy, then derivative of this with respect to y would be another x. So there that is. So that's your left-hand side. All right, let's see what the partial of your n is with respect to x. So what's that going to be? Okay, 4, good. No, wait. I disagree with that for a moment. Okay, here's why I disagree with it. Because remember, we're taking the partial with respect to x. So this e to the 2y hasn't got any x dependence on it. That just treats like a constant. So you got 2 e to the 2y. That's all a constant times x. Derivative of that is 2 e to the 2y, right? Okay. Partial of this with respect to x now. Again, you got a product rule. So what's that going to be? Okay, if you take the derivative of x with respect to x is 1, write down cosine minus cosine xy. Okay, and then do the other one. Minus, okay, x. Okay, only minus sign, so that changes that minus to a plus. Sine of xy, and the partial of that with respect to x is y. Why not? Okay, and then the partial of 2y with respect to x is 0, because that's a constant. Y is, you treat it as a constant. Okay, now let's see what we got. This, that, this, that, this, that. Sure enough, those are equal to each other. Ding, ding, ding. We can do our thing here. Okay? What's our thing? I think I'm going to erase what we already have done. That was just to see if it meets the criterion. It does, so therefore we can use our procedure. Okay, so since this is just, you've already confirmed it, you're not going to use that again anywhere. So let's get that out of the way. And what's the rule for solving this? You assume there is some function f of xy such that the partial of this with respect to x is your m. Remember, that's how we began, right? So let's translate that here. That would be the partial of f with respect, and that's of xy, okay, is equal to let's write down your m, e to the 2y minus y cosine xy, and then we're going to put our dx here. That's what we got from multiplying this over there, moving this over there, right, in differential form. You integrate that, you get f of xy. You integrate this, and what do you get? Remember, you're integrating with respect to x, so you treat your y as a constant, so what does this give you? Say that again. You may have said it right, I just don't hear well. Okay, it's that times x, because that's just a constant. Integrate that, it would be times x. Oh, man. E to the, so I'm going to put the x out front, x e to the 2y. Okay? Now let's integrate that with respect to x. Okay? And the y is just a constant, so put it out front. Antiderivative of cosine. Sine. And this is just like the y is a constant there, so it's xy, but then you would divide that by y, right? Your constant. Okay? If you don't believe me, take a derivative of this with respect to x. The y is out front, and derivative of this, 1 over y, move that here, they cancel out, right? Derivative of this is cosine xy times y, and so the y shows back up again, all right? So, basically, these go away, all right? Except for one thing. Your integration constant, which is now a constant function of y. So plus g of y, whatever that might be. Some function of y, because you didn't integrate anything with respect to y, so you could have, so there's your first step, okay? Now the second step, that was by using this, the partial of f with respect to x has to be your m. Now we do that the partial of n with f with respect to y has to be your n. Well, this is your f now. So take the partial of that with respect to y. No. Why did I put the integral there? Okay. This is a derivative. Is taking the partial of this with respect to y. Okay? So let's do it. And we want this to be n of xy, which is 2x e to the 2y minus x cosine xy plus 2y. That's what we want it to be, okay? Goodness gracious, my eyes are stinging like crazy. So let's take the derivative of that with respect to y. Partial. First term, x e to the 2y. That all of it? Wait. How about a 2? Chain rule. You're taking the partial with respect to y, you have to get that. Okay? That part's okay now. Let's see, did I do everything I was supposed to there? Let me make sure. Yeah, I think I did. Okay. So, partial of that with respect to y would be a little louder. Okay. Yeah, derivative of sine is cosine, so you just keep the sign the same, SIG and sine the same. That'd be cosine of xy times, second, x. Okay, because derivative of your argument there, the chain rule part would just be the x, because you're taking derivative with respect to y. Okay? And this would then be plus g prime, derivative of that of y. Right? Okay? Over here, we want this to be 2x e to the 2y minus x cosine xy plus 2y. Okay? Well, guess what? This one and that one, ding ding, they work. This one and that one, exactly the same. So this leaves us d g dy is equal to 2y. So what would g have to be? Second? Y squared. Yeah. So g of y must equal y squared. Right? Right? If derivative of g is 2y, then g itself must have been y squared to begin with. Okay. So, let's go back to our f, where we had it written down somewhere before we did this, and we had that f of xy is equal to x e to the 2y minus sine xy plus y squared, plus your g of y, which is y squared. And this thing here is equal to your constant c. There is your solution. Now, this is an implicit solution. Can you write this explicitly for y? No way. How are you going to separate that? How are you, it's going to be even hard to separate that. And this one wouldn't be too bad, but not with the other. So that is your solution. And that is really all you can do. Okay? And I was using G, they were using H, I'm sorry. Whatever. Anyway, we have x e to the 2y minus sine xy plus y squared, and they say plus c is equal to 0. It doesn't matter what sign you give the c. That was supposed to say equal to c. I don't know why they decided you can put the C, you can put it as a plus C is equal to 0 if you prefer it that way. It seems to be how the book wants this one. The last one, they had it equal to C. This time they put it plus C equals 0. So it doesn't matter which way you do, okay? So anyway, there's your solution. And we got the same thing they did. All right. Goodness. Earlier today, I just had a sneezing fit, and my head just started floating like crazy. And suddenly now my head is all clogging up and it's aching like crazy. But do we have time to do example 3? I don't think so, unfortunately. I wish we had, but actually it's better than where we left off last time. So we'll start next time with example 3. That will be an initial value problem that then you'll be able to figure out what C is. Okay. So we got a little ways done today. Homework exercises here. You can do any of the odds 1 through 19. And I think either 21 or any of the odds 21 to 25. You can try working on some of the others if you want to, but I think we'll see more of that kind of stuff later. So you can hold off of there until we get there. Make sense? All right. Sorry we got started a little late today. And I hope to be able to, let me also say this. I've told some of you in the previous classes, this is the last week of the first mini-term, meaning that the weekend is going to be mid-term. So that means usually the first week after midterm, they typically ask for samples of student, no, goodness, I keep saying that. They ask you to do, they ask me to do midterm progress report. Now, quite often they don't ever get around to even asking it, but in case they do, I would like to have some score from you. Now, I didn't say this in the morning class, so I should have. So if you haven't turned in something in each of your classes, please get something in, either your paper or your first test. Preferably both of them, okay? But if not, at least get one of those in by Monday, okay? Because that's when they're going to ask for midterm. The earliest they would ask a midterm progress report, sometime next week. So if I have it either Monday or Wednesday, that'll be fine. Try to get me something. If they don't ask, I'm not going to tell. But if they do ask, I do need to let them know how you're doing at midterm. And if I don't have anything, I have to say you're failing at midterm. I don't want to say that. All right, good deal. We'll go on and end this.